Class E amplifier that we have discussed before. We have discussed the operation of Class E amplifier, the efficiency of Class E amplifier, and the analysis using the nodal equations V1 and the currents through the load. So assuming that the L2C2 series circuit has a very high Q, so that you obtain a nice sinusoidal waveform. Okay, so it acts like a band pass filter, having allowing a single frequency to pass through, such that the current through the load is also sinusoid. Okay, so IRL is nothing but the same waveform divided by the same waveform that you see over here. So having amplitude V or peak divided by RL. Okay. Let's use these design equations that we have discussed before. So I've given these equations. I've collected these equations in one slide. So now let's see if we can design this Class E amplifier for a given specification. So my specifications are design a Class E amplifier to produce 1 megahertz 12 volt peak sine wave on a 50 ohm load, okay, using a 12 volt power supply. So what the question says is that we have a VDC of 12 volts, okay, and what is desired is to have an output that is again equal to VDC about 12 volts, okay. That is expected because of a high Q LC circuit, and this is again 12 volts. So that is desired, and the load resistance RL is 50 ohms, okay, over a load resistance of 50 ohms. This is 50. So what we do is let's set a value for Q. I mean, it's up to you. You can, but if you have to design, you set a Q that is high. So let's do it for 10. Okay, 10 is a high Q. So we have a high energy storage effect in LC elements. So look at this equation for a series RLC circuit. So your Q is omega L2 omega L2 over RL. So we know what RL is, and we have specified the Q as 10. Okay, so this is equal to 10, and omega is 2 pi into 1 megahertz. So what we need is a sinusoid having frequency of 1 megahertz. Okay, so this LC combination is supposed to resonate at this frequency, so that at this resonance frequency, the series L2C2 components, they're effectively shorted out. Okay, so you recall that at resonance, series LC is a short circuit. So if you calculate this, this will give you, what is RL. Okay, RL is 50 ohms. Omega is 2 pi into 1 megahertz. Okay, that's specified frequency. Q is 10. So this gives you L2 of about 79.6 microhenries. Okay, let me write this. 79.6 microns. And this design component, you can see over here in this schematic. This is an ADS schematic I've constructed. So you can see this L2 is 79.6 microhenries, and how it comes is that you are assuming a very high Q, and from the Q of 10, you evaluate L2 as 79.6 microhenries. Now for the RF choke, where is the RF choke? You see over here, this RF choke, it has a large inductance. Okay, so now what this expression says is that this implies that we are looking for a choke with an inductance that is L1, that is 10 times of L2, right? You can see this from here, because this is QRL, and what we have seen over here is this was 10 times of RL, right? 10 times of RL. is 50. Here we have 100 times RL, so that means at the same frequency your choke inductance is 10 times of L2, okay, and this implies that you're looking for L1 that is around 0.8 millihenries, okay, 0.8 millihenries. It's a large inductance, and you see, if without any loss in generality, even if you set it to, let's say, 1 millihenry, okay, practically, which is more convenient to find and to plug in the as an RF choke over here. So over here, if you use 1 millihenry instead of 0.8 millihenries, there won't be any difference in the circuit performance. So what I mean is that the current that flows out of these RF choke has a very small AC component, because this is going to choke any AC signal. Okay, so it's going to be a DC current. This IDC, it will be a DC current. So there won't be any AC component, right? Because you see, the at DC, this inductor is a short circuit. Okay, but for AC, the inductance is huge, so it's going to choke any AC signal, and you should expect a constant current through this probe. Okay, this probe is going to measure a constant current. Right, now how to calculate C1 is we use the second design equation. Okay, you recall this equations for C1 and C2. We evaluated them by evaluating the ratio of this node voltage V1T in complex form divided by the this series current IRLT. Okay, and if you recall, the result was the impedance. Okay, the result was the impedance seen looking from the side of capacitor C1. Okay, so if you look at the impedance from here, let's call this C, and this C is nothing but J omega L, right? So you have this is J omega L2. What do we have else? So we have minus J over omega C2, and the last term is plus RL. Okay, so that's what it is. So you see, the node voltage is V1. Okay, that is the capacitor C1. That's the same node voltage at the switch. Okay, at the JFET switch. Divided by the load current gives you the impedance. Okay, and from this impedance we have these two equations, because you see it consists of C2 as well, and the V1 is going to consist of C1, because it consists of these components, right? So if you want, you can skip back some slides, or you can watch the previous lectures to see how we have derived these equations, right? So let's use these design equations. You see, this is 1 over omega C1 is 5.45 times of RL, and this, if you calculate 5.45 into RL, then from since omega is 2 pi into 1 megahertz, this gives you a C1 of around 584 picofarads. I think this came out to be 584 picofarads. So it's a straightforward calculation. Once you know that these are the design equations, you use them to find the component values. Okay, so this is 584 picofarads over here. So this is your C1, right? Then you use the next design equation. So you have L2. Okay, you have C1 as 584 picofarads, and this equation, the third equation, is going to give you C2 as about 360 picofarads. So I think we have all the components now. The other way of calculating C2 could be, now, okay, so if you recall, we had some design constraints. The design constraints were that we had a 50% duty cycle. Okay, if you recall, we had a 50% duty cycle, and what we assumed was a sinusoidal case. So if you have a sinusoidal input waveform, okay, then at pi the switch closes. At pi the switch closes. At 0 the switch is open, Okay, so what we were doing, we were enforcing the condition such that once the switch closes, your V1 is 0. Okay, and in between you had the cycle, a rounded pulse, which was about 2 VDC, and then again once the switch closes for another half cycle, V1T goes to 0. Okay, so based on these conditions, these constraints, we have this equation for C1 and C2. But the other way of looking at this scenario is that if you calculate the resonance frequency of the series L to C2 circuit, we have the resonance set at 1 or 2 pi square root of L2 C2. And if you can guess this right, well, this must be equal to 1 megahertz precisely, but it turns out that resonance comes out to be equal to about 0.94 megahertz. So there is some deviation. There is little deviation in the required frequency. Why? Because we had those constraints. We had the constraints on the V1T node voltages. Okay, so if you recall, what I'm saying is, so for in evaluation of V1T, let's find it out where we had this constraint. So if you recall, the switch will be opened when sine omega t is positive. It opens at t equal to 0, closes at omega t equal to pi, and then we use this. For example, we integrated this equation with respect to dt to find v1. Okay, and then we use the constraints. So you see, we evaluated v1t by integrating the current through the capacitor C1, and we found the phase as well. So we will expect a phase difference, okay, phi, which depends on the current through the choke, on the load resistance as well, and the output, the peak output. So based on this, on these conditions, that V1T will be 0 at the instant when the switch is closed. If this condition is met together with the first differential, that is 0 as well, this condition is met, the frequency of the amplifier can be shifted somewhat without seriously violating the condition that at the half cycle when the switch closes, V1T has to be 0, V1 has to be 0. Okay, so we have a small shift of 0.94 megahertz. Again, it's not a problem, that's all right. So let's see, at the circuit, we have this 360 picofarads as C2 over here. So we have all the components. Now, if you look at this schematic, I have modeled this JFET by a voltage controlled switch. This is a voltage controlled switch, and here there is a model. Okay, and I've set the resistance R1 to 0.5 ohms. Okay, there was another specification that the on resistance was supposed to be selected as 0.5 ohms. So the switching resistance is 0.5 ohms for efficiency of around 100%. Okay, so this is 0.5 ohm. Now this voltage is being the switching is being controlled at a frequency of 1 megahertz, having a peak voltage of 0.6 volts. So, and you see, for 1 megahertz corresponds to the time period of 1 microsecond. 1 microsecond. And for 50% duty cycle, the width of the pulse is 0.5 microseconds. So we have a 50% duty cycle. We have 50% duty cycle, right? With an amplitude of 0.6 volts. So let's look at this node voltage Vn first, which is controlling the switching operation. It's a voltage controlled switch. Okay, so it switches at 50% duty cycle, and then it effectively shorts once the switch is closed. It shorts V1, so V1 is 0. When it is open, you have rounded pulses. So what we are going to have is a current like this over here. Okay, and this will contain a DC, and this also contains the harmonic content. Okay, so the DC is the average. This is 0. Okay, alternatively, when the switch is when the switch closes, you have 0. Okay, the node is shorted out. So the harmonic content, so this DC is filtered out by the coupling capacitor C2. Okay, so you won't have any DC at the V out. You will have a nice sine wave, right? And The other thing is that the frequency is going to be selected by 1 over 2 pi and root L2C2, so you will expect the frequency to be around 1 megahertz. Okay, this will be 1 megahertz. This is what these components will do. And we have set up a harmonic balance simulation, single tone harmonic balance simulation with the order, the harmonics order are about 64. So let's have a look at the V in. You see over here we have 50% duty cycle. This is about 0.5 microseconds over here. The time period when the when you have the square wave, okay, and this is when you don't have any signal, you don't have any stimulus to the switch is open. Okay, so here the switch is closed, switch is open, and this is about, this period is about 0.5 microseconds, so 50% duty cycle. You can see it from here. The other thing is, once you simulate the circuit, you run the harmonic balance simulation. It is expected that the current out of the RF choke is essentially a constant. It's a DC, okay, because RF choke, this is a large, so L1 is large, L1 is large, so you won't have any AC excursions, okay. You will just be feeding a DC current through the probe that is over here. So you're feeding a constant DC current, okay, out of the RF choke. The other thing is, if you look at the output, well, first of all, you see a phase difference, which is about 89.84 seconds, because if you remember, VRL is a nice sine wave with the desired frequency omega around 1 megahertz, and then there is a phase shift. If you recall, we calculated this phase shift before. It depends on the choke current IDC. It depends on the load, which is 50, and this peak you can see is about 13 volts over 13.5 volts. If you calculate phase from here in degrees, this phase comes out to be about minus 32 degrees, okay. And this translates, if you consider the whole cycle to be of 360 degrees, then the time corresponds to 32 divided by 360, right? I mean, I think you will be able to calculate the phase. You have the load resistance, you have the V out from here, so this is your V out, okay. You have the DC from here. Just plug in those values. You will find the phase in radians. Just convert this to degrees, okay. So 32 over 360 multiplied by 1 microsecond, which is the time period. It's a time period. This gives you a time of about 88 nanoseconds. 88 nanoseconds. And you see this shift is visible over here at the start. You see this marker M6 is over here, and this shows a phase shift of about 89.84 nanoseconds, which is expected. This is the phase shift in the output voltage at the load, and similarly the same phase shift comes at the load current IRL. If you look at the harmonic content, you see this M2 is at 1 megahertz. This is 1 megahertz. This is 1 megahertz. This is the harmonic content. And if you look at the second harmonic, now I have 64 harmonics over here. Okay, 64. Why? Because I selected the maximum order to be 64, and I wish to analyze the harmonic content of the output. You see the other harmonics. So this is the fundamental, which is expected, and that's 22.207. Then the second harmonic, which is indicated by the marker M3, is about minus 26 dBs down the first harmonic. So you look the value from here and you go over here. You see this is minus 26 dBs down. So the second harmonic is not all that important in magnitude. Note that the plot is in dBs. Okay, so the third harmonic and fourth harmonic up until 64th harmonic, these amplitudes are not important. They are not much contributing into the output time domain signal. Okay, so they have a very small amplitude. They have a very small magnitude that is contributing to the output signal. I mean, even the second harmonic is 26 dBs down the first harmonic. So 32 or 35 or 40th harmonic, they don't count much. Okay. So these are the results of the design, what we have earlier calculated the values. From from the values that we have calculated. And this trend, okay, we have the node voltage V1. Where is V1? Look at this node voltage V1 and the capacitor C1. Now, once the switch is closed, you see over here, once the switch is closed, the V1 is 0 over here, okay, V1 is 0. So switch is closed means the transistor is conducting, okay, so the switch is closed, we have voltage controlled switch is closed, then we have closed switch situation over here as well, so V1 is shorted out due to a very small resistance R that was 0.5 ohms, it was a short circuit. So we in these regions we assume negligible current that flows through C1. Instead, all the short circuit current flows from here, so there is nothing goes here. Over here, the switch is open. Okay, here the switch is open. So you have this pulsating trend in V1. Okay, and which is due to the opening and closing of switch. Since we are treating JFET as a switch. So this is about 50% duty cycle, and here again you see this is about 50% of duty cycle. So the harmonic content is as such. We have DC, okay, we have the other harmonics. So for example, second harmonic is considerable as compared to the first harmonic and third harmonic. So the harmonic content is significant. It's not a very nice sinusoidal wave. That is, the fundamental is more pronounced. We don't have anything like that over here. So this is about half the time period. Okay, half time period for which the switch is closed. Then for the other half cycle T/2 switch is open, right? So this trend actually constitutes this harmonic content, which doesn't show a sine wave. Okay, we have DC as well, and this DC is at 0. This DC is at 0. So that's how the design is. So what you need is the specification of what do you want, how much frequency do you want at the output, what should be the sine wave, peak, okay, the load specifications, what is power supply specification. If you're looking for a sine wave, for example, nice sine wave, then you must start with a very high Q. Okay, you need a very high Q so that there is enough energy storage, and you don't have any loss in the amplitude of sine. So it should be a sine with a constant amplitude. Okay, and then frequency can be selected from either this combination of L2, C2, but since we have constraints on V1, since V1 of T is 0 when the switch closes, okay, so this is 0 when the switch is closed, otherwise it is pulsating, so that is a closed switch condition. Based on these two conditions, so if this is I think this is about 2 VDC once you have open switch. Okay, so based on this condition for half cycles, we have these two equations for C1 and C2. Okay, and from there we can calculate these C1, C2, and correspondingly you have those L2 values. Just plug it in and find the C1, C2. So these conditions are derived earlier as well. You just use the design equations, find the components. Okay, set the circuit like this, and you can get the desired results of sinusoid with the phase shift, whatever comes out due to the constant current, load specifications, and the output voltage. And then you can look at the harmonic contents as well. So that's about it for the design. So okay, very quickly, where do we use these circuits? Now, if you recall and remember that the all three class C, D, E, unlike class A or AB amplifiers, which provide less efficiency but high fidelity, class C, D, and E amplifier are all about high efficiency. Okay, they are high efficiency amplifiers, and we've discussed this in chapter. They are narrowband and non-linear. Okay, so they're synchronizing, or you might call that they produce an arbitrary waveforms. So they are ideal for producing, for example, conventional signals like AM, pulse, or phase modulations, especially for radio broadcast signals from cell phones. Okay, using very low battery or electricity, because they're again very highly efficient. So, for example, for AM and FM broadcast transmitters, they have historically used Class C amplifiers with vacuum tubes for high power in excess of 6 megawatts. And this type of transmitter is still being widely used. So, the tubes are available. Vacuum tubes are available with maximum plate dissipation of up to 1 megawatt. And if you recall, Class C amplifiers have an efficiency that goes up until 90%, 85%. So a single large tube can provide an excess of 6 megawatt of RF power. Uh, Typically, a typical radio broadcast is about power requirement is about 2 megawatt, but amplifiers for Class C oscillators for much higher power, they are found in industrial heating applications. Okay, since they are very efficient and they don't lose much power, so you can save some, you can do some saving on electricity, and they can use for industrial heating, such as curing plywood and welding applications. Okay. Now there are many new designs that use Class D and Class E solid-state amplifiers modules with power from multiple modules being combined to achieve the desired total power, okay, at an efficiency of around 100%. So these switching amplifiers, Class D and Class E, they benefit from advances in transistor technology and have reached gigahertz frequencies. Now, if you recall, Class D amplifiers, they have a very good or a very high fidelity output sine waves, and they're very popular in applications like handheld audio devices, portable home theaters, mobile phones, etc. So where all in these cases, output must be a decent in terms of power and fidelity. So Class D amplifiers can provide a very nice or decent. Similarly, Class E amplifiers can provide very nice sine waves if you are looking for a very high QLC circuits. Okay, similarly for Class D, they both have a series LCR circuits, LC resonating circuits. Now, if they are very high Q, you have a very nice sine wave. So they can be used in mobile phones, handheld devices, and the size must be as small as possible for portability. So these are some applications of Class C, D, and E amplifiers.